We also spent a fair bit of time discussing centripetal force and centripetal motion for constant circular motion. So basically, if an object is orbiting or moving in a circular path at a constant speed v, then there is going to be an acceleration directed towards the center of the circle, and the circle has a radius r, and that acceleration is equal to v squared over r. It's always directed towards center. That's why it's called a centripetal force. That means center-loving force. Or a centripetal acceleration, for that matter. Now, the acceleration, including the centripetal acceleration, is going to be caused by the centripetal force. And the relationship between the two is still Newton's second law that you've come to know and use throughout the semester. That the centripetal force is equal to the object's mass. The mass is the mass of the object moving in the circular path, times the centripetal acceleration, or, if you like, mv squared over r. And the centripetal force is not a new force, it's whatever force we know is acting. It could be friction, it could be gravity, it could be tension, it could be the normal force. We've seen all three, or actually all four of those, that act as a centripetal force in different circumstances. Some examples of centripetal force we've seen are roller coasters, where you have the normal force and the force of gravity acting down on the object at the very top. Both are actually contributing to the centripetal force at that point. It's not a constant circular motion in this case, but it is still is a centripetal force. It's a force pushing the object towards the center of the circle, which is the normal force, and some combination of it and gravity, at least at the top, certainly. And that's one example of one that we saw. Another one is swinging an object on a string overhead, where the string is some distance and you're swinging it in a circular path, and it's following that circular path with some speed v. And in this case, it was the tension of the string that was associated with centripetal force, the string tension. Okay, so you have to know the speed of the object in order to find this, and you have to know the radius, and you have to know the mass of the object, and you can know what the centripetal force has to be. Other examples also are orbits, where we combined this equation, where gravity was the centripetal force, and we used the equation for gravity, that Newton's law of gravity, which basically says that it's equal to mass 1 times mass 2, or mass 1 times the mass of the object, where when you have gravity, of course, you have two objects, one with a bigger mass, one with a smaller mass in the cases we've discussed, and the smaller one orbits the bigger one in approximately a circular path. But m1 times m divided by r squared times this constant g, that's equal to mv squared over r. And then we got rid of this little mass. Little mass didn't affect the orbiting of the object. We also could multiply both sides by r, and we got just one r down here. So the equation became g times the mass of the big object, like the Earth, divided by r equals v squared. All right, so that was an equation for orbits that we had. But it's difficult sometimes to measure the speed of an object in an orbit. It's easier to measure its period. So knowing that the speed of the object is equal to the circumference divided by the period, we rewrote this equation as g times the mass of the big object, which could be Earth, divided by r is equal to 2 pi r over t, that quantity squared. And then we came up with the orbital equation from that we used quite a bit. G times the mass of the big object in the center divided by 4 pi squared is equal to r cubed divided by t squared. And then we use this to solve for whatever we're interested in solving. Usually we might have known how far the orbit is the object is from the center of the of the Earth, that would be r, and we're trying to figure out how long it's going to take it to get around, that would be t in period in seconds. Or maybe we knew t and we're trying to find r. But now you have the means of finding all of these, and you would need to use the constant capital G, 6.67 times 10 to the minus 11th, and the mass of the bigger object that's being orbited. Maybe it's the sun, maybe it's the Earth, or maybe it's some other planet. We looked some of those up. There's some videos where we looked at all that. And then we solved for whatever quantity we were looking for here. So we spent a fair bit of time looking at orbits. Other topics that we discussed include ramps. All right, when you have a ramp, an object on a ramp, we looked at the forces acting on the object on a ramp. There's the normal force, that's always perpendicular. Force due to gravity, it's pulling the object down. That's without friction. That was the first case we looked at. And what was interesting to us is we derived, if this is the angle theta for the ramp, we derived the acceleration of the object going down the ramp to be equal to g sine theta. All right, and then we added friction. We said, okay, if you have a ramp with friction, this was a good review of our friction content, and you're interested in the acceleration down the ramp. Well, the forces acting on the ramp, we still have the normal force, and we still have gravity. But we also had the force of either static friction or kinetic friction. Now, if it's static friction, that means the object's stationary. And I do want to remind you something about static friction. Remember, static friction is going to be less than or equal to mu s times Fn. Sometimes I might ask you to find the static friction acting on an object, and people will multiply mu s times Fn. That isn't necessarily the static friction. That's the biggest the static friction could be. But static friction can be less than that. For instance, let's say that this object the ramp had an angle of 0 degrees. Okay, if the ramp had an angle of 0 degrees, and let's say somebody's pushing on it with a force of 1 Newton, but that 1 Newton force is not enough, let's say, to cause the object to slide because the static friction is too great. So I might ask you, what's the static friction in that case? Well, in that case, the static friction has to be equal to the force, the size of the force applied, 1 Newton. Now, if this, that has to be true for static friction, that it can only be equal to the other forces acting on it. It can't be bigger than them. So you're not going to have a static friction causing the object to accelerate up the ramp. That just wouldn't make sense. Static friction is limited by the size of the force acting on the object. So if you have an object on a ramp, let's say, the ramp has an angle theta here, and the object is not sliding, static friction is going to be equal to Fgx. It's not going to be equal to mu s Fn. That's going to be bigger than Fgx. So static friction can't be that size. It can only be as big as the force acting on it. And then the biggest it can get, of course, is mu s Fn, so that when Fgx gets bigger than this, then the object's going to slide. It'll break static friction. Okay, that's just a little reminder on static friction that I thought is useful to reinforce. And of course, once the object breaks static friction and starts sliding, if the angle's great enough, that'll happen. The object will then slide, and we derive this with an acceleration equal to g sine theta minus mu k g cosine theta. This is the equation for acceleration of an object down a ramp when there's kinetic friction. After static friction is broken, then you'll have kinetic friction. And of course, without kinetic friction, you'd be back to the same old acceleration you had earlier. With kinetic friction, the acceleration is going to be smaller than it had been without friction. Okay, one more video after this.